This one's really short. It's only 2 minutes long, but it's a review of like kinetic molecular theory, which hopefully you did last year. Do you remember anything about that? No? Do you remember anything about solids, liquids, and gases? Little bit? Okay. This is going to be a little reminder for you about solids, liquids, and gases. So let's take a look at this.
Hi. Let me tell you about the states of matter at the molecular scale. That is, a scale that our eye cannot go to.
I'm really not happy about the narration, but we'll go with it.
Hi. Let me tell you about the states of matter at the molecular scale. That is, a scale that our eye cannot go to. I chose the example of water. The water molecule is made up of an oxygen atom and 2 hydrogen atoms.
What do you notice about the solid as opposed to the liquid as opposed to the gas? I'm just going to press mute and we'll just watch. So tell your partner anything you notice that is different about the solid and liquid and gas. Jerry, Kimmy, are you discussing what's different about? Okay, can you do that later? Thank you. What's up with the solid? It's just sitting there. Yes? And if you were to put it in a beaker, let me grab a beaker. So if I have a beaker and I have my little solid, look, that would be an ice cube, but we are going to use an eraser because I don't have an ice cube on me. If I put it in the beaker, does it take the shape of its container? No. So let's just go back and take a look at our liquid. If I was to take some liquid water instead of solid water and put it in my container, would it take the shape of the container? Yes. Would it completely fill the container? Not unless I filled it all the way up. But how about a gas? Does a gas fill its container as much as possible? Yes. Okay. What do you notice about the motion of all these particles? What are the solids doing? Solid particles doing in terms of motion? Nothing really. I mean, if they were more accurate, they would show them jiggling a little bit. Okay, they would just vibrate a little bit. What's the liquid doing? The liquid is just sort of it does what a liquid does. They flow, yeah? They flow past each other, la, 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 la. Okay, so everyone, you're going to be a solid with me. Be a solid. Show me solid. Show me liquid. Show me gas. Okay, which one takes up the most space? The gas. Solids and liquids actually take up a very similar amounts of space compared with one another. Okay, so if you have a tablespoon of water and you freeze it, it will actually become a little bit bigger because water gets bigger when it freezes. Most things don't, but they'll be similar in size. But a gas takes up a huge amount more space. Okay, anything else useful here? Not really. This is steam. more steam, more steam. Okay, that's it for that. Good. So we have dealt with now 3 of the 4 states that you should know about in grade 9. You should know solid, and the symbol for solid in science is, we put it in brackets, and we write the letter S. Okay? I meant to put that in red, but that's okay. Solid. Liquid, put it in brackets. Can you put that away, please, Velva? Thank you. Liquid. Or, if you prefer, you can just put the line for an L. I like to do the L because it looks like an L and not a 1. 1s kind of look like L's and L's kind of look like 1s. And then finally, well, not finally, we have a gas. And that's how we show them. So if I had some water, H2O, most often water is a liquid water. We have one other state, and that other state is called aqueous. Ignore my fancy A there. My pen is just doing weird things. Aqueous. Anyone want to guess what aqueous means? Dissolved in water. Yep. Can you see the word aqua in aqueous almost? Aqua for water, so it is dissolved in water. And the symbol for it is AQ. Can you think of something that can dissolve in water? Sugar can dissolve in water. What else can dissolve in water? Salt can dissolve in water. Do you guys know the formula for table salt? Salt is NaCl. And if we have salt water, we would have NaCl aqueous. Okay? Because it's dissolved in water. Yes? What if it's dissolved in something else? What they'll do is they will usually put, like, let's say we had CO2 and it was dissolved in hexane, they'd put hexane, just like that. Okay? But water is by far the most common solvent, thing that dissolves other things. And so it's the one that we deal with, like, most often in chemistry. Yeah. All right, so we have solid, liquid, gas, and aqueous. So if you're looking for examples of these, you might have iron, which is a solid, Fe. Did you guys know that iron is Fe? Maybe you've heard that before. H2O solid, that would be ice. NaCl, table salt. And if you're wondering what table salt looks like, if you could blow up table salt huge, big, you would have alternating sodium chloride, sodium chloride, NaCl, 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 NaCl in a cube shape, which is why salt forms little cubic crystals. Can you dissolve iron in water? No. Can you melt iron? Yes, you can melt iron. Does anyone know the term molten? Have you heard the word molten? Molten lava? What is molten lava? It is melted rock, okay? If we have molten iron, that means melted iron. And we would show that by writing Fe, and then we would show that it is a liquid. Okay? And of course, we're used to water being a liquid. That's just a normal thing we observe in everyday life. But you can actually get liquid sodium chloride, and we're going to watch a video a little later showing someone actually heating things high enough that the salt itself actually melts. Okay, so we'll take a look at that in just a bit. Gases, for example, we have helium, which is a gas. You're familiar with that in balloons, right? HE gas. Water vapor, that's like floating around in the air right now. You're breathing in water vapor right now because the air has some water vapor in it. And oxygen gas. As for aqueous things, we already talked about salt water, but how do fish breathe? How do fish get their oxygen? They get it through their gills. What goes through their gills? Water. So where is their oxygen? It's actually dissolved in the water. And so we have O2. For the fish, it's aqueous. For us, when we're breathing, O2 is a gas. And then we have HCl, which is hydrochloric acid, which we will be playing with a little bit later on in this class. All right. Everyone always asks about this, so I put it in, but notice I have put it in brackets. I put it in brackets because you are not responsible for this. Plasma is essentially a gas. It's a gas with a charge. Charged particles. Okay? And it's really hard to get plasma in the science classroom. All right? So we don't deal with it very much. All right? So that's why we don't worry about it too much. Okay. Please tell your partner what you think the difference is between liquid and aqueous. Liquid versus aqueous. What is the difference? Chat with your partner. What is the difference, liquid and aqueous? Well, that sucks. Anyone want to share what's the difference between liquid and aqueous? Yes. Shh. Liquid is liquid. Okay. So far, so good. Okay, so liquid is melted. Okay, whereas aqueous is dissolved in water. And water is a liquid, so aqueous things look liquid, but it's because the water is the liquid. Okay? Yeah. So you could have this crystal here, and we could melt it. All right, and you remember I said it alternates sodium chloride, sodium chloride, sodium chloride. The sodium is positive. That is sodium. And the chloride is negative. When you melt it, there's nothing else there. There's just the sodium and the chloride. But now, because it's been melted, these particles can now move. What's different about that between the melted and the dissolved? What's in the dissolved container that's not in the melted container? Water. So in this one, we have Na plus and Cl minus and water, H2O. And these particles, though, they can still move around. And just to let you know why we don't do very much melting of sodium chloride in the classroom, you have to heat it to 800 degrees to get it to melt. But if you just want to dissolve it, it just is like 20 degrees, okay? Here's what happens. Instead of having a nice crystal structure, if you melt it, they all start moving all around. And then over here, it is aqueous. Here's a connection to a later unit. This is going to be our electricity unit. And I might as well haul out the conductivity apparatus right now. So in order to have current electricity, in order for a current to flow, you need to have the movement of charged particles. Okay? So actually, I'm going to start with an ionic compound that is a solid. So we're going to have a solid. And if you don't know what an ionic compound is, don't worry, you'll learn about it later. Compound. And it looks like this. It's got a positive alternating with a negative and a positive and a negative and a negative, positive, negative, positive, positive, negative, positive, negative. Does that remind you of anything you've seen today? Yeah? Okay, so this is alternating positive, negative, positive, negative. I'm going to go grab us a crystal. This crystal here is called copper sulfate. Isn't that pretty? Lovely blue color, okay? Absolutely gorgeous. Everyone always asks me if they can eat it, but no, you can't. It's actually very toxic if you were to try to eat it. The formula of copper sulfate, if you are interested, is Cu and then an S. Do you guys know what Cu stands for? Cu is copper. And then we have an S. What element is S? Sulfur. And then we have O. What element is O? Oxygen. And then we have a little number 4 down at the bottom here. Okay, and this SO4 bit is called sulfate. If I were to put an S here, what do you think it would have attached to it based on this formula? Tell your partner. What do you think would be attached to the S based on this formula? Any guesses? What's going to be attached to that sulfur? Yes. Oxygen. How many? 4. Okay, so we have S, and we have an O, and we have an O, and we have an O, and we have an O. And that right there is sulfate. Copper has a 2+ charge. Sulfate has a 2- charge. Do you remember what I told you about nature liking things to be neutral? If you have a 2+ and a 2-, those two cancel each other out and they make that compound neutral. We have a whole unit on this later on in the course, okay? So you don't need to know that now, but it's just showing you that nature likes things to be neutral, all right? So this is copper sulfate. And so if this were our crystal, we would have Cu, SO4, Cu, SO4, Cu, SO4, Cu, SO4, Cu. Tiana. Now, let's remind ourselves. Current electricity is the movement of charged particles. You need charged particles that can move. Does copper sulfate have charged particles? Yes. Now, when it is in its solid form, can those particles move? No. So let's test that out just to make sure. I've got this plugged in. I'm going to turn it on. There are 2 wires here. Okay, and if something touches those wires that can conduct electricity, the light bulb will light up. I don't want to hold it just myself. I want something that will insulate me. Just in case. Okay. So here we go. Let's see. Does it conduct electricity? No. Super exciting, yes? All right. Now I'm going to grab some copper sulfate dissolved in water. Tell your partner, well, I get that. If it was copper sulfate dissolved in water, we would write CuSO4. What would we put in the brackets? Sorry, what? Can you drink it? No. It's the same thing. It's just been dissolved in water and it's fairly dilute, which is why it's not a darker color. Okay. It's basically, if we were to take this and dissolve it in water, this is what we would get. Okay. Now, what would we put in brackets here? AQ, aqueous. Okay. Now, let's remind ourselves, when it is aqueous, do you have charged particles?
Yeah.
Can they move?
Yes.
Yes. Let's see what happens. Hopefully, this will prove right. There we go. Okay, so you see, you can get conduction when you have an ionic compound. Ions are charged particles. So that's a copper ion and a sulfate ion. All right, I think that's enough of that. Just in case you're wondering, how about water? H2O. Water is a neutral molecule. Is it going to conduct electricity? Does it have charged particles? And can those charged particles move? It's a neutral molecule, which means its charge is 0. Let's find out what happens. Let's take a look. Water, here we go. That was just the two things touched. See, if they touch, it also does. But if they don't touch, does water conduct electricity? No. Okay. I'm going to turn this off so I don't electrocute myself. Unplug it so I even less chance of electrocuting myself. And we'll just put that to the side for now. Okay. So, according to this, which of the following can conduct electricity? Can the solid conduct electricity?
No.
No. The particles cannot move. And we just saw the aqueous. Can the aqueous conduct electricity? Yes. We have charged particles. Na plus, Cl minus, and they can move. So now I want you to predict what you think would be the case for the NaCl, the sodium chloride liquid. We're not going to actually do it because it would melt the wire because it would have to be at 800 degrees. But what do you think? By looking at this little picture here, could melted sodium chloride, liquid sodium chloride, conduct electricity? Tell your partner. Yes, we have charged particles and they can move. Okay. Excellent. Have you heard of chemical and physical changes? Chemical changes and physical changes. In a chemical change, you get something new. In a physical change, you get nothing new, it's just changed its form. Yeah, for sure. So if you take some ice and you melt it, do you still have water? And if you freeze it again, do you still have water? Yes. So is melting a chemical change or a physical change? It's physical because it just changes form from solid to liquid. You don't actually have anything new. And what if the water boils and goes up as a gas? Is that chemical or physical? That's physical because it's still water. It's going to condense at some point and come down as rain. Yeah? So even if you do something crazy, like you take some heat and you melt your sodium chloride and you get liquid sodium chloride, it's still just a change of state. If you were to cool it down again, you would get salt back at the end. Okay? If you dissolve salt in water, you'll get sodium chloride aqueous. So you start with sodium chloride. And you finish with NaCl. If you start with sodium chloride and you finish with sodium chloride, was that a chemical change or was that a physical change? That's a physical change, okay? So that is a physical change because it is the same. And if you taste salt water, what does it taste like? It tastes like salt because it's still salt. It's just dissolved. It has just changed state. It's changed its form. It hasn't changed into something new. Okay? So we're going to watch some dissolving of sodium chloride here. All right? So this is just a little up-close picture of what happens when we dissolve sodium chloride. Let's pause for a second here. There we go.
Placed in water. When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay, that's a lot more information than you need in grade 9. But if you remember, sodium positive, chloride negative. What do positives and negatives do? They attract. And that's why it alternates positive, negative, because the positive is attracted to the negative and the negative is attracted to the positive. Now, the cool thing about water is that if I have my positive, negative, positive, and battery low, okay, yes, just let me, there we go. Negative. If I have a water molecule, although this is a neutral molecule, these hydrogens are a little bit positive and the oxygen is a little bit negative. So what can happen is that the positive hydrogens, we can have a little water molecule come over here and say, hey, these positive hydrogens, what is wrong with this pen? Why is it like so faint? There we go. The positive hydrogens can come around that little negative ion. And what do these positives, all these little positives, do to this negative charge here? What do all those yellow positives do to that little negative? They attract it. And so what'll happen is they'll actually go and they'll surround it, and then they will pull it away. Okay? And so you'll end up with a negative surrounded by little positive ends of the water. Positive, 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 positive. So you end up with all the little yellow things surrounding the green thing. What do you think happens over on the other side? What do you think happens over here? Tell your partner, what do you think happens over here? Anyone got any ideas? We still have water, and water still has a positive end. Anyone got a guess? Yes. The oxygen, yeah, the oxygen end, which is negative. Okay, and I'm just going to draw the hydrogens without the pluses because they get irritating to draw. But you end up with those negative oxygen ends surrounding that positive ion, and they drag it away. And you end up with your little positive ion surrounded by the oxygen ends of the water, which are negative. Which is pretty cool. At least I hope you think that's pretty cool. And now, what we're going to do is we're going to take a little brain break. We're going to stand up and stretch, and then we're going to watch somebody melt some sodium chloride, because I can't do it for you in person because it's too dangerous, but let's stand up, have a stretch.
Wait, isn't that?
Yes. Yeah. Okay, everybody stand up. Oh my God, I'm being blinded by that thing. I'm going to move over a little bit. Stand up, stretch up high. Stretch over to one side. Oh. Stretch over to the other side. Stretch all the way back. Get your shoulder blades together. And now we're going to stretch forward. Oh, you know what we haven't done yet? We haven't done neck rolls. Should we do some neck rolls? So we're going to drop our chin to our chest and slowly go around in a circle. Slowly, 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 slowly. Do 2 or 3 of those. And then you're going to go the other way. Let's do some shoulder rolls backwards. 1, 2, 3, 4, 5, and then forward. 1, 2, 3, 4, 5, and then let's stretch our triceps because that just feels good. And our other tricep. And then our shoulders. And if you guys ever, like if you have a favorite stretch that you like to do, you can tell me about it at some point and I'll incorporate it in here. But we're going to do our little side to side massage. Side to side massage. You don't have to tap hard if you don't like it. You can just tap gently. I like a little massage there. And then we're going to go behind our head, behind. And then we're going to go in front and touch our opposite hip with our hand. And then we're going to sit back down and we're going to enjoy this video of mixing dry ice with molten salt.
3, 2, 1. Oh dear. Hey guys, I'm Nate. Welcome back to the backyard. Today we've got a fun experiment that we're going to try thanks to the suggestion of YouTube user Robert Vipperman. Robert wanted to know what would happen if we mixed molten salt with either liquid nitrogen or dry ice. Well, today is not the day for the liquid nitrogen test, but it is the day to see what happens if we pour molten salt onto dry ice. Well, we've got our foundry, we've got our salt, and we've got some dry ice. Let's try mixing them together. Now, as a first step, what we want to try and do is clean out our crucible. All of the crucibles we've got currently have residue from other projects in them. This one seems to have quite a bit of aluminum built up on the sides. So we're going to try and chip out what we can, then fire up the foundry and see if we can melt out the rest and shake it out so we have a mostly clean crucible to melt our salt in. We do want a small reservoir in our dry ice to pour the salt into so it doesn't just scatter all over the place. So let's take our drill bit and try and carve a hole down into the ice just a little bit. That looks toasty. Let's see how well molten salt pours out of a crucible. Huh. Well, it's cooled down. It certainly bubbled a good amount, but it didn't react horrendously violently at all, at least.
Do you guys know why it's bubbling? It's melting the ice, and that's not just any old kind of ice. That's dry ice. Do you know what dry ice is made of? It is frozen carbon dioxide. And carbon dioxide is a strange substance because when it is heated, it does not change into a liquid. It goes directly from a solid to a gas. So when the hot sodium chloride, liquid sodium chloride hits that, it causes the carbon dioxide to sublime. And when you sublime, you go from liquid straight to gas. And that's what's causing those bubbles, is bubbles of carbon dioxide.
It's not yet. I guess it's still possible to get there, but Even the salt that's just on our pavers has cooled down to being solid. Looks like our salt inside our dry ice has as well. Let's see if we can tip that out. Well, there you go, a nice solid chunk of salt right there. I think the salt in our crucible is still liquid. Try pouring a little bit more in. Skimming some of this aluminum off the top. It's just melting more aluminum as it goes. Whew. I certainly wouldn't want to get that on me, but it's nowhere near the violent kind of a reaction that we've seen in other people's channels where they pour salt into water. Ooh, the middle of that is still squishy. Definitely hasn't cooled down all the way. Very hot. Also very hot. Still both very hot. All right, now I know this is probably filled with aluminum and some other trace metals, but I'm gonna lick it.
It's another reason why we don't do it here. Because he can lick it.
Surprise of all surprises, it's salty. All right, now this is finally cold.
So was that a chemical change or a physical change? Physical change, because it started as salt, it melted, and then it re-solidified, it froze essentially, and it is still salty. Thank goodness I'm not doing that, because I would not want to lick that. It looks horrible, but it's probably just aluminum.
That one's a little less cold, but it's also a little bit thicker, and it was poured second, so that makes sense. Now, I'm gonna try and break a piece off of this dry ice. We're gonna see what happens if we drop this dry ice into some molten salt.
Any predictions if we drop the dry ice into the molten salt? Probably gonna bubble. Let's see.
Let's find out. 3, 2, 1. Bubbling, bubbling, bubbling. Kind of, not even a lot. Just a little bit of bubbling. I think the dry ice is disappearing a little bit faster than if you just left it out.
But this is so wild. Like I have trouble imagining salt as being liquid. Do you know what I mean? Like, and you just look at that and it's like there's a bowl of liquid salt. That's just a bizarre sort of a thing. It's so hot. It's crazy. Anyway, that's probably enough of that. Let us bop over. Yeah, let's do it. Let's see. There we go. And we're now on page 46. Okay, you guys know some of these already. If we go from solid to liquid, what do we call that when something goes from solid to liquid? Melting. What do we call it if we have something going from liquid to solid? Freezing. Those ones are easy. Okay, usually people like those ones. So if we go from solid to liquid, it's melting. Liquid to solid, it's freezing. What if we go from liquid to gas? Vaporizing or evaporating? What about if we go from gas to liquid? That's called condensing. I want you to think, Tell your partner about a time when you have seen something condensing. When might you see condensation? Okay. Question. Shh. When might you see something condensing? Can you think of a time? Rain. Yeah. So when you have there's water, there's gas up in the air and it condenses into little water droplets and those water droplets fall. How about when you're in the bathroom and the shower is on? What happens to your mirror? It gets foggy because there's water vapor in the air. It hits the cold mirror, and what does that water vapor do? It condenses. So that fog you see on the mirror is liquid water. It was gaseous water, and now it is liquid. Now, those are the normal ones. Here's the weird one. Do you remember what carbon dioxide did? Carbon dioxide did not go from solid to liquid. It went from solid to gas. What did we call that? Sublimation. Okay, I'm going to write that up at the top. So solid to gas is called sublimation. Sublimation. It sublimes. There is also a word for when it goes from gas directly to solid. And that word starts with a D. And what it's doing is it is depositing. So it's called deposition. It deposits. Deposition. Okay? All right. And we're just going to take a quick jump over to page 47. So we're jumping ahead to page 47. All right. And we're going to take a little look and see what happens when water boils.
Here's one of the biggest things that people don't understand in chemistry. Keep this in mind. When a liquid boils or evaporates to become a gas, the molecules don't come apart. So let's talk a little bit about liquids, evaporation, boiling, and molecules. So here is a very tiny glass of water. Well, it's a tiny glass of water that we've zoomed in zillions and zillions of times so we can see what makes it up. And what we see is that this glass of water is made of all of these water molecules. One oxygen atom connected to two hydrogen atoms. That's why we call it H2O. So our glass here contains lots of molecules of liquid water. Let's now make some steam, some gas water. What we're going to do is we're going to heat up this liquid water. And as we heat it up, the molecules in it are going to start moving faster and faster and faster until some of them are moving so fast that zoom, they can jump, shoom, right out of the liquid water, enter the air above that liquid, and start flying around. Now, these guys up here are molecules of steam, also known as gas water. So here's the main point. When they're liquid water, the molecules, H2O, are packed really close together. When they're gas water, or steam, they're still molecules of water, 1 oxygen and 2 hydrogens.
And that's why this is a physical change, because you still have, excuse me, those little Mickey Mouse shapes. It starts out as little Mickey Mouse water and it finishes as little Mickey Mouse water. It has just changed how it's arranged. Now, here's what a lot of people think happens. He's going to show you in just a moment.
It's just that now they're not as densely packed and they're flying around in the air above the liquid. Here is the mistake that so many people make and that I don't want you to make.
And this is
we said,
48,
is the
page
way
48.
that gas, that water does evaporate. Here's the mistake that people make. Here is another glass of water. So many people think that when water molecules become gas, that they have to break apart, that the atoms that make up those molecules split apart from each other. And that's the only way that the liquid water can become gas or steam. So we have these molecules here, and they have to rip these atoms apart. And so that if we were to zoom in and look at steam, we wouldn't see water molecules, but we'd see all of these pieces of the molecules, all these atoms ripped apart. This is wrong. Here's the big red X.
If that did happen, would that be a chemical change or a physical change? We start with little Mickey Mouses, and we finish with separate black atoms, the hydrogens, and red atoms, the oxygens. So is it the same substance as it was before? No, it's changed into a different substance. That would actually be a chemical change where you end up with new stuff. The atoms have rearranged into new things. And that's not what happens when we boil water. When we boil water, you still have water. You don't have separate hydrogens and oxygens.
I don't want you to make that mistake. On the other hand, here is the right way that boiling or evaporation happens. The molecules look just the same in gas as they do in liquid. They do not, big red X, they do not split apart into the atoms that make them up. Same in liquid, same in gas.
Okay, and that's it for that one. And let's just quickly go back to page 47. And here we have water molecules. Let's just fill in a few blanks and then I'll give you your homework. Okay. This is a water molecule. All right. And a molecule is a type of particle. A particle is just a tiny bit of matter. A tiny piece of matter. An atom is another type of particle. And so we have a molecule which is made of an O atom, oxygen atom. And it's also made of 2 hydrogen atoms. How many atoms is the water molecule made of? Tell your partner. How many atoms in total? How many atoms is the water molecule made of? 3. We have 1 oxygen plus 2 hydrogens. Molecules are always made of 2 or more atoms. We'll answer this question about the types of elements later. We haven't talked about that yet, so we'll come back to that. Okay? Did you guys learn about metals and nonmetals last year? No. Okay, then let's not talk about that yet. So let's just go down here. And if you are not interested in learning this black diamond thing, then you can start on the homework, which is page 40. No, hang on, not 40. Page 52 and page 38. Page 52 and 38. Now, for those of you who are interested, I'm going to go over this little bit about the atoms in a molecule. So if you're working on 52 and 38, you're going to do it quietly. If you've already done 38, then you're ahead of the game. All right. So here's the little enriched part. The atoms in a molecule are stuck together with very strong bonds. Bonds are like glue. This is page 48. Bonds are like glue. And what do they stick together? They stick atoms together. We're not going to worry about the covalent just yet. But when we have a water molecule, we have an O. And we have a bond. And then we have an H. Okay, so that right there is a bond, and that one right over there is a bond. When water boils, do the bonds break? No. Okay, the bonds are intact. But there's another type of force that is being broken. If you have one water molecule next to another water molecule, there are actually little forces each water molecule acts like a little magnet, okay? And this is called an intermolecular force. Intermolecular force. And if you're lazy, you might just call that an IMF. Now you remember that the bonds are like glue. Is it easy, like crazy glue? They're like Gorilla Glue. Is it easy to break Gorilla Glue or is it hard? Easy or hard to break Gorilla Glue? Hard. But if you have a couple magnets, I got a couple magnets here. They do stick together. Okay, but actually these are opposites. I've got them. Let's try this one. We're out of time. We'll talk about this next day. Okay, homework is 52 and 38. All right, let's see. Very nice. Okay. And just the only thing is that they don't pair off until they have to. Okay, so these ones would go 1, 2, 3, 4. And this one would go 1, 2, 3, 4. And this would go 1, 2, 3, 4, and then a single and a single. Yeah?
I forgot to show you the homework.
Oh, okay, good. Excellent, excellent, very nice.
The one from yesterday.
From yesterday as well, very good. Fantastic, thank you very much. This pencil has no lead in it. Let me find something that does right. There we go, that's better. Fernando. There we go, thank you very much. How are you? Good. Just playing with magnets.
Tomorrow, right?
Tomorrow, yes. What's that? We're gonna go over the Bunsen burner today. Finish up, just practice it.
Oh, and I was with you, bro. What do you want? Your shoes.
Oh, okay.
As a cat.
Okay.
As a cat.